Okay, so what I'm going to do here is do this derivation, this direct stiffness derivation. There we go. What? That's too much. So we're going to derive of this 1D beam element, okay? All right, so we're going to get the 4x4 K matrix. This is the 4x4 one, right? All right, this is what we started. Well, actually, I didn't start a class. I just kind of presented it. But here we're talking about beam element that can deflect as follows. It has 2 degrees of freedom per node, a V1, and a theta 1, and then a lateral displacement at node 2, and then also a rotation at node 2. And you have a force at node 1, an external force at node 2, and then also a moment at node 1, and then also a moment at node 2. We assume that the beam has an E and an I and an L, okay? So we know those things, all right? Looks a little funny. Okay. So the way we do this is kind of like a force method or a superposition method. If you think of a stiffness matrix like this, that's unknown, right? And in this case, this is our 4x4, right? This is our 4x4 stiffness matrix. Gets multiplied by a displacement vector, and that equals a force vector. If we assume a displacement, so we're going to assume displacements, and so for example, let's say we assume the following displacement, so that this is basically saying, if you look at this type of mode, everything is 0. Theta 1, V2, and theta 2 are all 0. The only thing that's happening is it's deflecting up 1 at node 1. So actually that beam basically looks something like this. All right? It's that type of deflection pattern. And we can actually figure out using, basically basic beam equations, what is the force and moment, and from that, you can get the deflection and the rotation at those points. All right. Now when you do that, what you get here, when you multiply this through on this side, is you just get this first column, because all the other effects go to 0. So this just becomes K11, K21, K31, K41. Likewise, if I use 0, 1, 0, 0, which looks something like this, gives you that type of deflection, I can extract the second column, okay? If I do 0, 0, 1, 0, that'll give me a deflection that looks like this, and I can extract the third column, and then finally the fourth column comes from 0, 0, 0, 1, which is deflection like this. Actually, it's the wrong way. I got it the wrong way. It goes like this, because you have a positive rotation at that node. Okay, although it doesn't deflect. And you can't see that because I zoomed out too far. So we're going to actually assume displacements, use mechanics and materials to get these right-hand side vectors for those displacements, and then that allow us to directly get the stiffness terms in terms of that, okay? So this is like similar to what I said. The stiffness matrix is basically like an influence coefficient. So what I'm actually doing is here is I'm saying, okay, as I move, keep everything fixed, and I just move the first degree of freedom, which in this case happens to be the displacement at node 1. How does that affect the force? That's what this first column does. Now, if I keep everything fixed and I just affect the rotation at the first node, that gives me the second column, all right? And likewise, if I look at just moving, displacing on the second node, that gives me the third column, and then if I look at the effect of the rotation, the influence of that on the forces, that gives me the fourth column. So that's the approach we're going to do. And I'll probably pause a couple times because it's a little bit of a long derivation. I might not go all the way through everything, but at least I'll set it up. All right, so to do that, I need to kind of know the solution to a couple of different little beam cases. So before we get started, I kind of need two solutions. I need to know if we have a beam that's fixed on the right-hand side and has a force applied, call it P, and then a moment applied, I'm going to call it M. From this, I want to be able to know what is the deflection at x equal to 0 and the rotation at x equals 0, okay, where this is x and this length here is L. So this is the point x equal to L, and this is the point x equal to 0. The other case I want to look at is when we're fixed on the left-hand side, and again we have a force acting up and also a moment applied, and I want to know how this, again, now we got this is x, so this is x equals 0 here. Now we want to know for this loaded situation, what is V at L and theta at L, the rotation and the deflection at those points, okay? So you can go through and you can integrate, you can get the bending moments and then integrate those twice, divide by EI, and get the deflection, and the first derivative gives you the slope. But since I talked about it in class, let me talk about this book. This is another way of doing it. Like, I really recommend this book. I think it's an excellent reference for most engineers. Let's hope that shows up. Something like that. Maybe you can see it. This is a newer version. I used to have an older version, but it disappeared from my office. And it just has a lot of stuff, so it's really useful. I mean, for example, well, what we're going to use it for is it has keeps going. Basically, at least this, I kind of stopped, but at least this many pages of beam and frame tables. So, of various loadings and constraints on beams and frames, and what are the resulting forces and moments and stuff, okay? Plus, it's, stuff with shells, flat plates, torsion with warp. It has a good coverage of stress concentration factors, warping parameters, and cross-sectional properties, and so on and so forth. So it's very useful. Even if you know how to theoretically derive these things, it's real easy to make a mistake. So I think it's actually a good idea to be able to, to have one of these books. So there isn't, as is often the case, the exact case you're looking for is not always there. And I don't know whether it is on this one or not, with a moment and a tip force. Yeah, it has some that are similar in that you have moments and tip forces that are at different locations. But it's really not a big deal because we're going to look at two situations. If this is from Rourke, and actually Rourke has this stuff going this way. So if we look at, we're going to look at actually two tables. One is, oh, it does have, wait, it does have, it has the guided, it doesn't have the, okay, so it has guided, but that's not really a moment. Right. Where's the one with the moment? Yeah, okay. So if we look at table 8-1, which is in section 8-17. This is the beam tables. And we look at case 1A. That is as follows. It looks like this. It has a beam bending down. It has a point here, W. That's at some distance, A. And has a length, L, and all that sort of stuff. So it's cantilevered. So it's close to this. It doesn't have the moment. And then, and in our situation, we're going to let A equal to 0. But then if I also look at table 3A, it's case 3A in the same table. It is bending moment here at some point, MO, where it's applied again at some distance A. Now, in both these cases, A is going to go to 0. All right, A is going to go to 0. All right, and in this case, we're going to change the sign of MO because, and the sign of W. So we're actually going to get P by setting P is equal to minus W, and in this case, M is equal to minus MO. So changing the direction of those. And then we're going to superimpose those two, and that'll give me the tip in the moment, okay? And what I want, again, is the deflection and the rotation. So if we go and look at this one, all right, this one gives me the deflection at A is minus W over 6 EI. This is at A, which is the left point. Times, setting the little a equal to 0, I just get 2L cubed. And then the rotation at A is equal to WL minus A squared over 2EI. So that's just pulling those right out of the book. Now we do the same for case 3A. And in this case, I get the deflection at A is MO times L squared minus A squared over 2EI. And the rotation at A is minus MO L minus A over EI. So they're close, but I have to do a couple of sign changes on this, and that's all I really need works for, so I can put that away, I think. And if you look at this, if we write this in terms of our sign conventions, because they have, well, there's kind of two things going on here. One is, you can see they've defined W down. They put the negative in here, so in fact, they've got the right sense of the deflection. They're saying negative deflection is down, but their force is, the positive sense of force is down. So I'm going to flip that. So we're going to get that the deflection, and I'll write it this way for this case. And I'll directly superimpose them. Let's directly superimpose them down here. So for this case, the deflection, let me use V because that's what we use in the notation, at x equal to 0, from this first part is going to be P on 6, well, I get a 3 because the 2 cancels with that. So I get 3 EI L cubed, all right? All right, now we add on to it this deflection, and our moment is changing sign, so this gives us a minus M L squared minus A, well, A, okay, I'm sorry, A goes to 0, so that goes away, over 2EI. All right? And did I copy those down? No, I got that right. Right? I got the right one. Right. Okay. So that's our deflection for that case. Let's box that equation. And then let's do the same to get the rotation. Okay, so if we look at the rotation term, again, we let A go to 0. This W changes sign, so I get a minus P times L squared over 2EI. All right? And then I add to it this case, and we get the sign change on that. So we get plus M times L over EI. All right? So I've added the two rotations, but I've done the sign change because my moments and my forces have flipped sign. Okay? Now this case is basically the same situation. It's just, I always forget what it is. It's, again, we have to worry about the signs, things flip around, and so on and so forth. But you know in this case that the deflection at L is going to have the same types of terms, PL squared, I'm sorry, PL cubed on 3EI, and then it's going to have an ML squared on 2EI. Now the question is always, which are the signs, because we have different sense of rotations, and well, actually the bending moment diagrams flip. So you can go back and rederive all that stuff, but I think the easiest thing is just to do, you know, think it through. I'm kind of actually a big proponent for engineers to be able to do like thought experiments and figure out what's going on. So if you just consider the tip force, right, what should be the sign in that term? Well, it should obviously be positive, because if P is a positive value, the deflection goes up, right? Now on the moment, should it be a positive or a negative? Well, again, it should be a positive, because if I bend in that direction, right, if I have a positive moment, it's going to toe it up like this, and it's going to deflect up. So both of these should be positive. Likewise, on the theta side, let's write the two terms and do the same type of thought experiment. PL squared on 2EI, and then you have the ML on EI term. All right, again, if we just consider P, if we put P up, you know, in the positive sense, that will give you a positive theta rotation, so that should stay positive. Now the moment also does the same, right? If you put the moment on in that sense, what you're going to see is it's going to give you a positive theta, so this should also both be positive. So we got this one associated with this case, and then associated with the other case, we have the, where are we? The deflection at 0 is PL cubed on 3EI minus ML squared, that's L, on 2EI, and then the rotation is minus PL squared on 2EI, and the moment part of that is PL on EI. All right, so we're going to use those two cases, all right? And we're going to use those in these situations to back out the 4 columns of the stiffness matrix, okay? All right, I'm going to pause the video here, and I will pick it up in the next video.